Do a little bit of an example about rearranging equations and how that's kind of relevant to kind of the scientific method, as it were. So again, where basically this transposing is basically we're just taking an equation that's got lots of terms in it, and one of those terms is not on its own, and we're basically rearranging that equation so we can get the thing we want to know equals and then equation. So making the thing you want to know the subject of the equation. Okay, so in this case, if we might have a circle of area A and an equation that describes that, okay, pi r squared, and we might want to rearrange that to get to make r the subject, and that's all we're doing in rearranging the equation. I think this then goes doesn't go through that, but basically you have to do this is. Whatever you do to one side of the equation, you must do to both sides of the equation. Okay? So in this case, you might divide both sides by pi to get a divided by pi, and then r squared on its own. Okay? And then you would have r squared equals pi over a, and then you take the square root of both sides. That would leave you just r on one side, and then the square root of a over pi on the other side. Okay? So it doesn't really matter what order you do stuff in. Okay, you could take the square root of both sides first, okay, which would give you the square root of a equals the square root of pi times r, and then divide by the square root of pi, and then you'd have the square root of a over the square root of r, square root of a over the square root of pi, and that would be the same as the square root of the whole fraction. Okay, so but whatever you do, you always have to do the same thing to the left and the right hand side. Okay? Golden rule. Okay, I think this goes through. Okay, so okay, so this explains what I've just said. Okay, and then we square root both things. So again, we're just going to think about rearranging to make the x the subject of the equation. So in this case, we've got an equation 5 equals 3x plus 2, and this is kind of quite a common you'll come across this type of equation a lot, because this is very similar equation to y equals mx plus c. So if, for instance, you were working in a lab, okay, like you will be doing in Evolution of the Living Earth, and you've got some standards, so you've got the concentration of something, okay, some element you're interested in measuring in the environment, say phosphorus, and you've got a bunch of different standards of different concentrations, and then you will put them in a machine, and that machine will give you some measurement of how intense the signal is from each concentration. So signal up there. Okay, so for low concentration samples we might have less response, and more concentration samples we have more. We might be able to draw a line through that, okay? And then we could work out the equation of that line, okay? So that would be an equation of y equals mx plus c. But then we might have some things we don't know the concentration of, so we put that in the machine, and that gives us a signal up here, okay? And we want to turn that into a concentration, okay? So to do that, okay, you could draw a graph, and then you could draw a line across here and draw a line down there. But you can do it mathematically, which is a lot more precise. So if you know the equation of the line, okay, then you've got this formula here, y equals mx plus c. Okay, all you have to do is we want to get x. Okay, so equal something. Okay, so we could, similar equation. This equation here is the same as this equation up here. Yeah, pretty happy about that. So the first thing we want to do is we want to isolate the x as one thing. Okay. So the first thing we might do is we've got plus c over on this side. So if we take c from both sides, okay, c minus c is 0. Okay, so plus 0, that would go away, and then we'd have to have minus c plus y on the other side. Okay? Or you could write that as y minus c equals mx. Okay? And then to isolate the x, we would just divide both sides by x. Okay, so that, oh no, not x, you idiot. By m, well remembered. Okay, so that then gives us, this cancels, so it gives us an equation y minus c over m, that's an m, equals x. So we've transposed or rearranged that equation to make x the subject. Okay, so in the example on the board there, we take 2 from both sides, that would give us 3 equals 3x, okay, and then divide both sides by 3, and then x is 3 over 3, which is 1. Okay, so that's an example there that we've just gone through here, except A is M and B is C. Okay, we're just using different thingies. Okay, so why don't you guys have a go at, oh, I haven't turned top hat on. Let's not worry about that. Okay, so have a crack at that one there, if you can. So rearrange that equation to see if you can isolate just x. Happy times. So in this case here, can you see this? Okay, so we're going to take away b from both sides first. So y minus b equals ax squared. Okay, then we can divide both sides by a. That makes that go away. Okay, and then we can take the square root of both sides, giving us x is the square root of y minus b divided by a. Okay, so that's rearranging equations. Now this is an example of that. So this is the pole vault world record through time. So this is the male pole vault record up here, just over 6 meters. Female pole vault record is here, around 5 meters 20, something like that. My personal best is here, which is a long time ago now. But one question you might want to ask as a scientist is, what's the highest that it is possible to pole vault? So it's not a question that many people ask, but it was a question that I was asking when I was stuck at kind of 4 meters 32. Okay, and there's some hilarious gifs of stuff that happens when you try to figure out how high you can vault. I think this one's a particularly... oh, yeah, we've all done that one. And this one is the most painful of all. Oh, yeah, that's uncomfortable when that happens. So one of the things we need to do now as a scientist is, if we want to know how high it's possible to pole vault, we need to build a model. Okay, so the model that I'm going to build is I'm going to basically take all of the energy of a running person. Okay, so how fast a person can run, we can work out how much energy they have, and if they convert all of that energy into height, okay, then that would be a model that might be able to describe how fast a person could, how high a person could pole vault. Okay, so here are some kind of equations which help us do that. So the first one is the kinetic energy of a moving object. So this is how much energy an object has because it's moving. So this describes how much energy a pole vaulter has as they're running down the runway with their pole in their hand. Okay? And the other equation, the gravitational potential energy, is the energy required to move something from one height to another height. Okay? So the model is this third equation here, that all of the kinetic energy that you have, you convert that into gravitational potential energy. Okay? So that's our model. So our model is that a half mv squared, where m is the mass of the pole vaulter, v is their velocity, is equal to mgh. Okay? So we need to rearrange this equation to work out what the maximum height is. Okay? So we need to basically make h the subject of that equation. Okay. So this is a relatively trivial rearrangement. I'll just move that up there, and then we'll be able to draw on the board. Okay, so all we need to do is divide both sides by m and by g. Okay, so that leads that and that cancel out, that and that cancel out, that and that cancels out. So that leaves us with an equation, a half, that's how you write a half, v squared over g, yeah, or v over 2g, could be your equation, equals h. Okay, I quite like this equation because it means it doesn't matter how heavy you are, that doesn't affect your ability as a pole vaulter. There are other things that affect one's ability as a pole vaulter that I no longer have, but weight is not one of them. Okay, so that's our equation now. So all we need to do now is plug in some numbers into that to figure out what the highest beacon pole vault is. Okay, so we know G is 9.81 meters per second squared. Okay, and we know that the velocity of the fastest human on Earth is 44.72 kilometers per hour, which is quite fast. Okay, so first of all, because I've given this in crazy units, so this is in SI units, this is not in SI units. Okay, if we want to work this out and not end up with an awkward number to play around with at the end, we're going to convert the kilometers per hour into SI units. Okay, which is this, so 44.72 kilometers an hour is 44.72 times 1,000 meters per hour. Okay, there are 1,000 meters in a kilometer. And then we need to divide, because it's per hour, we need to divide by the number of seconds in an hour. Okay, the number of seconds in an hour are 60 times 60, 60 seconds in a minute, 60 minutes in the hour. Okay, so that, if we do that, we get 12.42 meters per second. Okay, does that sound about right for how fast someone could run? If you think about how long it takes Usain Bolt to run the 100 meters, it takes him about 10 seconds. If we're going to do our guesstimation thingy, okay? So if it takes 10 seconds to do 100 meters, how many meters per second is he going? Overall, 10 meters per second. Yeah? So this answer is kind of broadly correct in terms of it fits with our understanding of how the world works. Okay, so we've got 12 meters per second, we've got 9.81 meters per second squared for E, so we can work out the theoretical maximum height a person could pole vault is 7.86 meters. Okay, so if we look at what that would be, okay, so I guess first of all, that in the model, that's the amount of height your centre of mass increases from when you're running to until you go over the bar. And when you're running, your centre of mass is not on the ground, so it's kind of maybe 1.2 meters off the ground, something like that. So you've got to add that on to the 7.86 meters, which kind of suggests that we would have a world record somewhere around 9 meters. Okay, which is considerably harder than the world record is now. Okay, so this means that that's probably not a very realistic model that we've used. So this is the part when we go back and reassess our model, okay, so if we can build in extra factors, because our simple model fails the scientific method of kind of comparing it to data. So all kinds of things could be wrong with this. So we're basically assuming 100% of the energy is converted. When you do pole vaulting, there's actually a little hole you put the pole in, and that would take away some of your height. So there's all kinds of extra factors that go into how high you can actually pole vault, which we build into your model. Okay, so that was kind of an aside, really, but just to reiterate the importance of rearranging these equations and how they can be useful either in things like simple stuff like working out the concentration of stuff in environmental samples, but also answering questions about pole vaulters, which is probably less relevant to you. Okay, so back to these quadratic equations. So this is kind of where we finished off yesterday. So these are all kinds of quadratic equations, different flavours of them. But it's really something where you've got the variable that you're interested in. It's x in all of these, but it could be anything. It could be t, it could be phi, it could be q, anything. One of them is squared, and then there's addition and subtraction terms where there's a singular one and a one with x to the power of 0. Okay? And all these are different types. So what we're going to do now is for the next lecture or so, go through how we go about solving these equations. Okay. So if you want to go back and see if you can solve those later on in the course, those are good examples to try and work through. So they have this general form where there's x squared, x to the power of 1, and then x to the power of 0. And in front of each one of those, there's a constant. Okay. So to start off with, let's just assume that the first one is a constant of 1. So there's no number in front of the first x. Okay. So it turns out that we can express any equation that's of that form, x squared plus some number x plus another number. We can express that as two brackets like that. So we can basically work out. So we went through how we go from, if we had two brackets like this and we expanded those brackets, we would end up with a formula that looked like that thing at the top. Okay. Where these two numbers at the end are some number, nothing to do with x. They're just a number, and those can be whole numbers or they can be fractions of numbers. Okay, so these two numbers at the end turn out to be really critical in solving the equation. So those are important. So just to go through kind of reiterate that process we did kind of last time. So if we start out with an equation that's got these two brackets in it, where x plus a number and x plus a number, we start to multiply out those brackets. Okay, first of all, we split one of these up into x and n in this case, and then times each one of those by the bracket. That's what we've done here. And then you multiply out those individual brackets. Just give something like that. Okay, and then we can start to join those things together and make something more simple. Okay, so this is kind of the final answer. So we've got 1x squared, we've got a number here, m times n, and if m and n are just numbers, you times them together, you'll just get a number. And then you've got m number of x's and x number of x's. So this term here is going to be x times the sum of m and n. M and n and m and n. Okay. So that's kind of that expressed up there. So for any quadratic equation that we have at the top there, okay, the term b, okay, b is going to be this number and this number added together, and c is going to be this number and this number times together. Okay, with that rule, we can start to think about how we would solve these equations. Okay, so so it's important here that we can think about if we can make an equation y equals something, x squared, a number times x, and then a number. If we can make that equal 0, okay. We'll go on to think about how we might do that. Very straightforward. If we can make it equal to 0, then that means that this times this also equals 0. Okay? And the way that we solve these equations is that if two numbers times together equal 0, okay, it must mean that one of those numbers is 0. The only way that you can times two numbers together and get 0 is if one of them, or both of them, are 0. Okay? So either that number is 0, and in that case, we can then very easily solve for x, because then we just need to rearrange this equation, take n from both sides, and then we end up x being number. Or the other one is 0, and then we take m from both sides, and we get. Okay? So we basically have to do something to figure out what these two are. If we've got this equation, or that equation at the top, we basically create these two brackets, we figure out what they are, and then we say one of them must be 0. So the answer is either one number or the other number. Okay, and this basically means that quadratic equations quite often have two answers. Okay, so if you look at this equation here, so this is one of the things, the equation for x squared plus 6x plus 5. Okay, so I drew this in Google. Okay, and you can see here that if I wanted to work out what that equation equaled when y equaled 0, okay, so it crosses y equals 0 at 2 points. Okay, so there would be two answers to that problem. Okay, so sometimes you would leave it there, say there are two answers. Sometimes with a quadratic equation, you would look at the two answers. For instance, if you were calculating a concentration based on a curve rather than a straight line, use a quadratic equation, you might come up with two different answers for the concentration of something. If one's a positive number and one's a negative number, you can't have a negative concentration. Okay, therefore you can use kind of your knowledge of how the Earth works to pick a correct answer out of the two. Okay, so I mean these are some examples, which I'm not going to go through now. I guess I'll just go through this one example here. This special case where it's called a perfect square. Okay, so what this means is that when you factorize that out and figure out what the two factors are, so that each bracket we would call a factor because you times them together to get the whole equation. Just like if you had the number 10, okay, that's got a factor of 2 and 5, you times those two together, you get the number 10. With this equation, there are going to be two brackets that you times together and you'll get this answer. Okay? So that one of the ways that we can kind of think about trying to solve these, because we don't have any number in front of this x here, so the first term in each of these brackets is just going to be x. Okay? Because when we multiply out those brackets, we're going to times this number by this number, okay, and then we're going to times this number by this number and this number by that number. Okay. So the first term is going to be x and x because when you times those two together, you'll get an x squared. Okay? So we need to think about, well, this, we've got something to go here and something to go here. Yeah? And we know that that number, which will be, let's call that one n and that one is m, when we times n and m together, we're going to get 25. Okay? So we need two numbers that times together to give 25. Okay? And when you add them together, you're going to get minus 10. Okay? So the only numbers that fit that are 5 and 5. Minus 5 and minus 5. Okay? So when you take 5 minus 5 plus minus 5, you'll get minus 10, which is this number. And when you times minus 5 times minus 5, you'll get plus 25. And this is called a perfect square because this expression is exactly the same as this expression. Okay? So it's kind of got the same size of each, kind of magnitude of each thing. So you can write that x minus 5 squared, if you so choose. So this is an example of a quadratic equation that will only have one answer. Okay, it won't have two answers. Because, well, it'll have two answers, but they'll both be the same. Happy times. And there's this other example here where you have this kind of difference of two squares, which basically means you don't have a number in there. So this is the same as writing x squared plus 0x minus 81. Okay, so when we're trying to solve that, our first thing is going to be x. Okay, and then we need a number that, two numbers, one that goes here and one that goes here. When you times them together, you'll get 81. Okay, should be pretty happy about knowing what that number is. And then when you add them together, you get 0. Okay, so the only way that you can add two numbers together and get 0 is if they're the same magnitude but different signs. So I can add plus 5 to minus 5, and that will give me 0. Okay, but to get 81, okay, 81 is 9 squared, so that has to be 9. Has to be 9. So one of these is a plus, and one of those is a minus. Okay, so that's a special case of difference of two squares, because difference of 9. Where that number, the 81, is a perfect square in itself. It's like a number, a whole number squared. You can use that to if you know all of your squared numbers, which is kind of not. You don't have to know all of the squared numbers. Okay, so we can solve these equations. Okay, we can factorize them and then rearrange each factor separately by the method that I've just shown there, by trial and error. Okay, by looking at the equation and thinking what number can I put in there that will be, if I times it by the two numbers together, it will give me the n number, and if I add them together, it will give me the middle number. Okay, so that's one way of doing it. There is a general formula that allows you to work all quadratic equations out. Okay, which is where x is equal to minus b plus or minus square root of b squared minus 4ac over 2a. Okay? You don't have to learn that, but it may well come up in the exam. We will show you later on how we get this equation. But I would, as you're allowed to take your notes into the exam, I strongly recommend that when this does come up in the lectures, you write it down in your notes. Get rid of it now so you can't copy it down. There were some whimpers. What was the whimper? So the exam, you're allowed to take your notes in, okay, not the book. So make sure important things are written down in your notes. Happy with that? So let's just go through some examples here. Okay, so 2x, I'm just going to move the board up a bit. So 2x minus 5x minus 3. Okay, so this one's slightly more complex. Okay, so in this case we've got two brackets. Okay, I've drawn them really big for no reason. So we know that there's going to be an x here, and an x there. Okay, but if we times that x by that x, we're only going to get x squared. Okay, so one of these has to be a 2. Okay, so that we'll get x squared when we multiply out the two brackets. Okay, so we now need to think about what these numbers are going to be. Okay. So if we just look at the factors of the end there, what are the factors of 3? Okay, the factors of 3 are 1 and 3. Okay, so these numbers are probably going to be 1 and 3 or 3 and 1. We don't know which one yet. But we now have to think about how we then will times these numbers together to get 5. And this 2 here, this 2x here, does slightly complicate things. Okay? So if we think about how we would multiply out this bracket now, let's just put some pluses in there for now. They're going to be wrong. Let's think about that. So if we multiply out this bracket, we're going to get 2x times x is going to be 2x squared. It's pretty good for now. Looking pretty promising. And then we're going to have 2x times 3, which is 6x, plus 6x. And then when we multiply out the other bracket, we're going to have x times 2x. We've already done that one. So we need x times this guy, which is going to be, let's do, which one are we doing? We're doing this one first. We're doing this, ignore those for now. It's going to be plus x, okay? And then 3 times 1 is going to be plus 3, okay? So this is going to be 2x squared plus 7x plus 3. So that's wrong, okay? Because it doesn't give us 5x. So we think about, well, if we think how we might, if we've got a 2x here, okay? When we times that by 3, that's going to give us 6x, okay? Now, we've got x times 1, so if there's a 1x going spare here. So if we can do it the other way around, if we can somehow take away 6x first, and then add 1x, okay, that will then give us our 5x. Okay, so if we actually think about how we deal with this, we would think, well, actually, if we make this, so when we times that one by that one, okay, if we make that a minus, okay, and I know it's not making this one a minus, because if I make this one a minus, then we'd end up with 2x, minus 2x times x, which would be minus 2x to start with. Okay, so that can't be the case. So in this case, we've got 2x squared minus 6x, okay, and then that times that is plus 1x, and then plus 1 times minus 3 is minus 3. That then simplifies to 5x. All that in there, minus 5x. So that is kind of how we go about kind of the process of narrowing down on the right answer through kind of trial and error. Okay, this explains it in some kind of detail. And there is the answers. Okay, so 2x plus 1, x minus 3. So that means that we can then say, well, if that equals 0, then 2x plus 1 equals 0, or x minus 3 equals 0. Okay, if x minus 3 equals 0, we just add 3 to both sides. So that's x equals plus 3. In this case here, a little bit more complex. Take 1 from both sides, gives us 2x equals minus 1. Divide both sides by 2. So then x is minus a half. Okay? So that's if you can make the equation equal 0. I'll just so I'll just give an example of how we go about manipulating the equation so it does equal 0. So if we had an equation y equals x squared plus 1x plus 5, that was the equation we had, and we wanted to solve that when y equals 2, okay? So if y equals 0, we would just use this approach to solve it, okay? So we're basically asking to solve this equation. 2 equals x squared plus x plus 5, and all we have to do is rearrange the equation so we get 0 on one side. And in this case, one side has got 2 on, so we just minus 2 from both sides. Minus 2 from both sides. So that becomes 0 minus 2. Okay, so 5 minus 2 is 3. Okay? Then you would try and solve that equation. Now this particular example is an equation which is a lot harder to solve than the one, because the ones that we've used so far have whole numbers here. Okay? So you can solve them by trial and error that way. Not all quadratic equations have whole number have whole number answers. Okay, so like the ones that I showed yesterday that ended up producing the golden ratio, that doesn't have a whole number in. Okay, let's go through this one. So 3z squared, so we're dealing with a z now rather than x, not really matter. 17z plus 10. Okay, so we need to find a number that you times them together to get 10. Okay, but when you add them together, after you've timed them by the factor of 3 up there, okay? So in this case, we know that you get 17. So we've got 3z and z are going to be our starting positions. Okay, and then we've got factors of 10. So our factors of 10 are 1, 2, 5, and 10. So we can multiply those two together to get 10, multiply those two together to get 10. Okay, we've got a 3 here. We're trying to get 17. Okay, so we can kind of go through that process of kind of trial and error again. Okay, so let's try thinking about what if we had maybe 1 and 10 in here. Okay, so 1 times 10 will give us 10, and then we've got 3z times z is going to be z squared, 3z squared, sorry. 3z times 10 is going to be 30z. Okay, and we're going to have a 1z in here. So we add those together, we'll end up with 31. We might be able to do some trickery and get 29. So it's probably not going to be 1 and 10. Okay, but if we look at the numbers here, we know that 3 times 5 is 15, and 2 is times 1 is 2. Those add up to give 17. So if we can choose our numbers wisely here, so we want this 3z term to be times by the 5. So put the 5 over there, and the z terms to be times by the 2. Put that in there. And then we're trying to get plus 17z. Okay, so this is positive, this is positive. So if we times this by that, we'll get 15z, so that will give us a plus there. Times that by that, that'll give us 2z, so we want that to add on to that. So if we then were to multiply out this set of brackets, that times that gives us 3z squared. Then this times that gives us plus 2z, and then this times that is going to give us plus 10, and then this times that is going to give us plus 15z. Okay, then we can start to simplify that together again. So this z term, that z term can be added together to give us 3z squared plus 17z plus 10. Okay, so that's the process we go through for basically for, that's what I said there, all that stuff. We ended up with 3z plus 2 plus times z plus 5. Okay, and then you could solve each one of those in turn. Okay. This is another example of that. So this is quite a horrible looking equation, right? You're pretty unhappy with the look of that. Okay. So the task here is to try and simplify that. Okay. So the first thing we want to do is, we've got this quadratic term at the bottom. Okay. The first thing you want to do is see if you can factorize that. Okay. To try and make the equation more solvable. Okay, so in this case, let's do that. Okay, so we just need to. So the first term, 2x. Okay, that has two factors, 2x and x, gives us 2x squared. It's the only way that we can get 2x squared. I guess they both could be minus. Let's not deal with that. And then the factors of the last term, so just minus 9. Okay, so the only ways of getting minus 9 are minus 3 times 3, 3 times minus 3, 9 times minus 1, or minus 9 times 1. So that's what we've got to work with. Okay. Okay, and in this case, the answer is this down here, 2x plus 1 minus 9. And if we start to work through why that is, okay, so we're timesing 2x times minus 9 is going to give us minus 18. Minus 18x. And the 1 times plus x is going to give us plus 1x. So minus 18x plus 1x is going to be minus 17x. And that's what gives us starting with it. So that allows us to then simplify this whole equation here to whatever it was, x minus 9 all over x minus 9, and this one is 2x was it plus 1? Yeah, plus 1. Okay. So that's actually made the equation a lot easier because this term now is exactly the same as that term. So they cancel out. So we then end up with 1 over 2x plus 1. Okay? Much easier to solve. Okay? Okay, so I think we'll stop there for today, but what we'll do is we'll go back and we'll just do some of those examples. Okay?